Thank you, Brian. So this talk is actually Colby's talk, and Colby couldn't be with us today. He just got a job as a fish biologist. So good for Colby. We're proud of him, and hopefully I can do my best to give his talk for him this morning. So today I'll be talking about how sampling gear can affect population dynamics. And so population dynamics, of course, is very important because that's ultimately how we manage our fisheries, right? Humans, as we know, we're very good at catching and exploiting natural resources, and we see that with the birds, turtles, big game, big fish, and the American bison. And we've seen that over history, the impacts of human exploitation. So this ultimately leads us into the topic of my talk today. So channel catfish, or just catfish in general, as you guys have heard through and through during this whole meeting, are very important fish, right? They have a recreational importance. People like to fish for them. But they also have a commercial importance, right? So very economically important fish. And so given all of that, evaluating the population is the next step, right? It's an imperative step into characterizing and better managing our catfish populations. Because of this double-sided interest for channel catfish, right, we can have both recreational and commercial exploitation. But ultimately, what we want to do is protect from overexploitation, right? And in order to do that, we have to get at the vital rates, or the population dynamics, recruitment, growth, and mortality. But before you even do all of that, you got to have a representative sample from your population, right? And so when we think about population dynamics, graphically, it's births and growth or immigration that add to a fish population or fish stock. And then what leaves is deaths and immigration, and deaths, that can come in different forms. It could be natural, or it could be us, right? And understanding these rates at the end of the day is really important for getting at what fisheries are doing, understanding the basic patterns and the issues that are occurring in our system. Right? So recruitment, what I mean here is, reaching a viable size, becoming a viable member of the population. Growth is the addition of somatic organ adult tissue. And mortality, like I said, comes in two different flavors. It could be natural, or it could be fishing. And really, at the end of the day, vital rates gives us better informed decisions, and it can infer into if we need management actions, such as minimum length limits or slot limits. And of course, population dynamics vary by species and by location as well. The general paradigm that we see is if you have something that can grow fast and a lot of it dies, right? We say you can have more liberal regulations. Whereas you have something that grows slow and, is not dying as much, you got to have very conservative regulations, right? And so that's like the field mouse versus the elephant thing. But for us, really, the goal is to prevent overfishing. And overfishing comes in two different flavors as well, growth and recruitment. So growth overfishing, fish are being whacked before they can reach a decent size. Relative to recruitment overfishing is where we're whacking them before they can even make more of them, right? So management, there's a lot of species and a lot of locations, and we need to be adaptive about how we manage our species, right? We can't have this blanket, one regulation fits all thing. And so as managers, we need to be able to allocate our time effectively and get proper reflective samples of the population. Get a good representative sample in order to inform better decision making. So the objectives of our study were to quantify the catch rates of channel catfish using various gears, evaluate differences in length frequency, right? And so that's going to get at what kind of a view are we getting of the population? And additionally, take all that data and then generate population demographics and see how those values may vary given those different gears choices. And so we were presented with this awesome opportunity to look at data from a long-term data set collected by various state agencies as a part of the long-term resources monitoring element for the upper Mississippi River. So here we have our 6 locations along that upper Miss gradient. And all of our fish came from Lake City, Minnesota, La Crosse, Wisconsin, Bellevue, Iowa, Alton, Illinois, Cape Girardeau, and Havana, Illinois. And that's actually on the Illinois River. So the LTRM utilizes a suite of gears and employs a stratified random sampling to get good coverage of all available habitats. Sampling was conducted from June 15th to October 31st, and ultimately we analyzed data from 1993 to 2018. The gear we chose to evaluate was electrofishing, large hoop nets, small hoop nets, and tandem, as in both set together at the same time. Electrofishing is standardized according to LTRM protocols. It's a pulse DC, power goal at about 3,000 watts. Each run is about 15 minutes and covers approximately 200 meters. Large hoop nets are fished with the mouth of the net facing downstream. The first hoop is 1.2 meters, and the mesh size is 3.8 centimeters, and these are all baited with soybean cake. We see the small hoop net's a little bit smaller. It's 0.6 meters at the first hoop, and the mesh is 1.8 centimeters. And again, these are baited with soybean cake as well. And then, of course, the tandem is the combination, this paired deployment of both the large and the small hoop net. And again, those are the dimensions of the nets there. Okay, fish, of course, were collected, measured and weighed. And of course, the field personnel also took other various environmental variables as well. Otoliths were removed and processed using methods from Bucknard 2002 and aged by 2 independent readers. Any discrepancies were sorted out amongst the 2 readers. We had to standardize all of our catch per unit efforts, right, across all those gears. And what we did was, for comparing the gears, we assumed equal effort in terms of personnel time, the time required to deploy each gear was expended, we assumed equal. And all of our analysis we did an ANOVA to compare all the catch rates. And then further, we did a Tukey's honestly significant differences test to assess those pairwise differences. We did average length of the fish, and then length frequencies were compared using a Kolmogorov-Smirnov test. And for all you old guys, we did everything in SAS. So overall, from 93 to 2018, we collected down near 40,000 channel catfish using the small hoop nets, and then 13,000 using the large hoop nets. And those in combination, of course, come up to 53,413 channel catfish that were caught using that paired deployment setup. And electrofishing collected about 12,000 catfish. All right, so let's kind of dive into this. All right, so when we looked at the ANOVA, they suggested, catch rates were different amongst all the gear types. We see that small hoop nets had the highest catch rates, and then the tandem had about 3.48 fish per night. Large hoop nets caught about 1.79 fish per night. And of course, electrofishing had the lowest. So here we see the groupings here. So when we look into the length frequency distributions of all of our gears, there's some things that we need to know. Electrofishing here. Yep, we're missing. There's something weird going on here, right, for electrofishing. When we look at small hoop net, we're kind of missing those fish out towards the larger ends. Kind of makes sense, it's a smaller gear. Large hoop nets, conversely, we're missing that smaller size classes, right? And then, of course, when you look at it tandem, it's like, whoa, all right, now we're actually starting to paint a picture here. When we look at the Kolmogorov-Smirnov test, the KS test, we see that, we had a statistically significant result, and we see that small hoop nets rarely captured fish over 400 millimeters. So right there, you can see small is in that orange line. Further, electrofishing rarely caught fish between 100 and 300. So that's kind of weird. I don't know. For some reason, we weren't collecting fish there, and you could see that in the length frequency distributions earlier. Here, you're looking at average size of fish collected per gear. We see that the small hoop nets were 254 average, and then the large was 444, so it's larger. And then somewhere in that happy medium is the tandem hoop net with the average size there. So let's look at age, and I think age too is going to kind of reflect what we were seeing with the length frequency. We see that with the large hoop nets, we're missing these year classes, right? In our sample, we're not able to collect 1, 2, and 3 effectively, evidently. Small hoop nets, we do have the 1s, the 2s, and the 3s, but we don't have anything passed into the older age classes. And then again, somewhere in that happy medium is the tandem hoop net setup, where we're kind of seeing more of that widespread distribution there. So when we look at the von Bertalanffy growth models generated by all 3 of these gear types, we see that, there's pretty good fit, but there's implications here. The L infinity, when we look at the large hoop net, is 692. But for the small hoop net, it's 605. K is about the same for both, but our L infinity is very different. And then again, somewhere in that happy medium, when you put the 2 together, we get a whole different L infinity value of 711, and it's a tighter fit there in our von Bert. Again, when we look at catch curve, estimating mortality using our age data, we see that when we use just the large hoop net, we're getting a lower mortality estimation than when we compare using the small hoop net, where we're getting a little bit higher mortality estimation. And then again, somewhere in that happy medium, using that tandem setup, we see that mortality is really somewhat more in between the small hoop net generated mortality and the large hoop net generated mortality. And so, a little cut off there. So really at the end of the day, our gear types provided different catch rates, right, amongst all of our gears. The von Bertalanffy growth and catch curve, the R-square values were highest when we calculated it using the tandem setup. Slowest growth was seen using the tandem hoop setups. And I don't know why this didn't show up, but in the Gallucci and Quinn paper, what they did was they took L infinity multiplied by K and another value, I'm sorry, I can't remember. But that they were using that as a function of trying to compare the growth, and we see that growth was slowest when we used the double or the tandem hoop nets. Ultimately, the tandem hoop nets and the small hoop nets provided the highest catch per unit effort, and then the tandem hoop nets provided really the widest distribution of sizes in our sampling effort. And then, of course, tandem hoop nets again provided the widest age range of channel catfishes as well. And with that, I have to acknowledge that this study was conducted by the U.S. Army Corps of Engineers Upper Mississippi River Restoration Program Long-Term Resources Monitoring Element. The LTRM is a cooperative effort between the U.S. Army Corps of Engineers, U.S. Geological Survey, U.S. Fish and Wildlife Service, Illinois Natural History Survey, Iowa Department of Natural Resources, Minnesota DNR, Wisconsin DNR, and Missouri Department of Conservation. And with that, I will take any questions. Yes.
And you've got marked fish out there, right? Because you did the population size estimate with marker capture.
No.
Right, that's not. Okay,
No,
I was
sorry.
hoping you were, because I wanted to see, we do a lot of this side-by-side gear comparison in
Mhm.
the field. I like the approach you're taking, and I like the conclusion you're coming to, because it's what I think is real, but it would be neat to know, is that tandem hoop net really what's out there?
Yeah,
I mean,
yeah.
It probably is, given the evidence you've laid out, but I was hoping you had marked fish. I was gonna suggest you go back and like chunk them into 100 millimeter bins or something, and
Mhm.
check your length frequencies against. I'm getting you confused with Steven's stuff, so, sorry.
No, that's fine. It would be cool though if we could.
Well, and this is awesome work too. Is this gonna be published in the proceedings as well? You know?
This will not be, unfortunately. But
I may be contacting you guys to, again, might be good to use some of what you found as we try to develop our tandem protocol here, because you've got some good information.
yes, right on. Awesome. Yes.
Time for more questions?
Yes.
Yeah, so if you extend this then to, you know, trying to set harvest regulations and things like that, how, I guess, you know, 50 or 100 millimeters difference in L infinity and difference in mortality, I guess how much does it change your depiction of what growth and mortality is like? Does it change it to the point where you might seriously consider different length-based regulations?
Yeah, I think I think maybe the next step then here is for us to develop these yield models using the inputs from the different gear, and then seeing how, you know, that sensitivity of the population changes as we model it, you know, using those various factors. But ultimately, you know, I think that conservative approach is, you know, what we're after. It's like, I guess that's the better, you know, the safer method, and I think, you know, that's kind of what we were able to do with the data that we collected, is that, you know, gives that more conservative estimate, if you will, you know. So, older fish, slower, you know, all that stuff. So,
Any more questions? Thanks.
thank you.